So one of the great things about learning Java and concurrent programming is the fact that there's almost always something new to learn. And as I was playing around the other day with the stuff we've been talking about the last couple times, I discovered some cool things that I didn't know were there before, and I figured out how to integrate them into my ever-evolving Timed Memoizer class. If you recall, the Timed Memoizer is the one that takes the memoization technique where we can essentially cache the values of stuff, of functions, in this case the prime number checker, and then add in support for timing out the keys when they haven't been accessed for a while. And so I'm going to show you the new version. It's really cool. It illustrates a bunch of new stuff that I had just learned about. So Timed Memoizer implements function. That part's the same, so we can transparently replace the memoizer for a function. Then down here we're going to have a concurrent hash map that's going to serve as the cache. This is now mapping key to something called a ref counted value. Future task has gone away, and all the complexity associated with using a future task has gone away, as you'll see. But the functionality that future task did is still here. It's just been it's been localized in a single function that's part of concurrent hash map, and that function is called compute if absent. We'll take a look at that in a second. Here's the function that we pass into the constructor to cache it, so we can use this anytime we need to compute a value. We're going to have ourselves a scheduled thread pool executor, which has a count of 1, so there's one thread that's running this thing. The difference between this implementation and the one we saw before was the one we had before, the earlier version, would create a runnable for every key in the map. So every key in the map had a runnable, and that runnable was timed. It was going to be timed out after a certain amount of time, and then that would run. So the issue there was if we had a lot of keys, we'd have a lot of runnables that the scheduled executor service had to manage. This new implementation is just going to have one runnable, and you'll see how it gets used in a second. There's a field called m non-accessed value, which is simply a ref counted value with a count of 1. We use this to simplify timeouts. You'll see how that works in a second. Here is ref counted value. Ref counted value is the replacement for the ref counted future task that we talked about before. And we no longer need to have future task for reasons I'll talk about in a second. So what this does is this just stores a value, which is a generic parameter called myValue or mValue, and it also has a ref count in it. And you'll see what that gets used for in a second. We have the constructor that sets those things up. We have the equals method. All the equals method does is check the reference counts to see if they're equal. This gets used in a clever way later with the concurrent hash map. Here's the get method. This simply increments the reference count by 1 atomically and returns the value. So it doesn't block. It just increments the count. Here's the constructor of Timed Memoizer. And this is quite different from what we had before. It's really cool. We go ahead and we stash the function here. And then we go ahead and we're going to create ourselves a runnable, which is a lambda expression. And it prints out we're about to start the purge of the keys that haven't been accessed recently. You'll see why we say that in a second. And then it goes through a map. It walks through every entry in the concurrent hash map. Now remember, concurrent hash maps have this property that the map is never locked while we're traversing it. So this works because we're only traversing in one thread of control, but the map itself is never locked. Only individual entries that are accessed will be locked for only the briefest period of time. So we're going to get each entry one at a time from the map, and then we're going to go ahead and we're going to store the current ref count of each entry. Remember, the reference count here is used to check to see whether or not something's been accessed recently. So we're going to store its old count. Then we're going to go ahead and we're going to try to remove that entry from the map if its reference count equals 1. If a reference count equals 1, that means it hasn't been accessed recently. So the way that the 2-parameter version of remove works is you give it a key, and it will remove the key and the value associated with that key if and only if the value equals the value that's passed in here. So what we're doing here is we're giving it a value that we pre-computed to have a reference count of 1, and we're saying, essentially, if this thing hasn't been accessed since the last time we ran through this loop, get rid of it. And atomically removes things. Now here's where things get subtle. So between the point where we try to atomically remove something, let's say that we try to atomically remove it, and its value is not 1. So that means it's been accessed recently. So between that point and down here, it might get incremented again by 1. And we want to be able to differentiate between, or by 2, or by n, right? It could get incremented because other things could be accessing that key. So we want to be able to identify a situation where we checked and it was not, the count of the item has not been 1, so we didn't remove it. But we also want to be able to determine between the point when we do that check and down here whether it's been incremented yet again. Because in that case, we want to make sure we do something special with it. So here's what we're going to do. And this is also a super, super cool Java 8 feature for atomic long. So down here, we're going to go ahead and look at the value of the entry that we're looking at. And we're going to check its ref count. And the idea is if the ref count of the entry is still the same as it was up here, then that means nobody accessed it in this window of time. So what we say is we check the value of the ref count, and if that value is greater than the original value here, that means that in between this point and this point, somebody in another thread has incremented this thing by 1. And if that's the case, if it's greater than, we keep the count, this new incremented value. Otherwise, we drop it back to 1. And when something has been set to 1, if it is not accessed again to the point where this loop runs once again, then we're going to remove it from the map. So this is just a really super clever example of what we'll call greater than compare and swap. So this is what we would call a greater than compare and swap, or a greater than cas. And we're doing this because of the fact we aren't able to lock the map for any period of time, because that's not the way that maps work. Concurrent hash maps don't work that way. So this is basically doing some magic to make sure that we set the count here properly for the ref count. So after each of the items has been checked, we go ahead and print end the purge of keys not accessed recently. Now, the question here is, when does this particular function or lambda run? And what we're going to do is we're going to schedule this runnable to run at a fixed rate in milliseconds. So we're going to say start running in 500 milliseconds, and then every 500 milliseconds run again. So what we're doing here is we're no longer putting a timeout on a per key basis, where you could have a lot of timeouts. Instead, we have one timeout registered, and that timeout gets triggered every timeout milliseconds, and it sweeps through every item in the map and checks to see if it's changed. So the net effect is roughly the same. It's just that we have a heck of a lot less timed runnables that we're trying to manage in our scheduled executor service. So it's going to scale, conceivably will scale up much better. And it turns out that you don't have to do a whole lot of extra stuff in order to make this work. So that's basically what that looks like. Here's the apply method. The apply method is much simpler than it was before. And the reason it's much simpler than it was before is we don't have to deal with future tasks in this implementation. And so here's how it works. The apply method gets called with the key. We look up in the cache, and we get a ref counted value, which is what the cache stores. If the ref counted value is null, that means we haven't entered anything in the map before under that key. And then we come down here and we call compute if absent. And compute if absent is this really cool Java 8 function that's part of ConcurrentHashMap that eliminates the need for all that future task stuff we had done before. And so what compute if absent does is it goes and it stores the key in the map, and if the key is not there, then it atomically runs this lambda expression. And what this does, and we'll talk more about this shortly, what this does is it goes ahead with the lock held, and it will run this once and only once for each key that's being inserted the first time. It goes ahead and makes a new ref counted value, applying this function to set the value of that ref counted value, and gives it an initial count of 0. So this thing gets run one time and only one time if the key is not in the map. So that eliminates all the need for the future task, which is what was doing that before. Under the hood, a future task-like thing is being used, but we don't have to know or care how that works. So this is a really cool function which will take a key, this key, and then go ahead and create a value that will store in the map atomically. And then when we're done, we just say rc value.get, and that calls the call up there that increments the reference count by 1. So that's basically the new implementation of the timed memoizer. If you spend time and go back and look at the old version, which is still in the earlier repository for scheduled executor service, you'll see how it worked. It's just more verbose and has a lot more calls to schedule timers to cancel individual keys. OK, any questions about that? Yeah?
So in the previous implementation, you were setting the timeout per key, but
right.
Here you're doing one for all of them?
Yes. So the observation is before, for every key, we had a timeout that the scheduled executor service managed, which worked fine, but if you had lots and lots of keys, you'd have lots and lots of runnables scheduled, so that could become an excessive memory utilization. This just has one timeout that just iterates through the list of the map.
Are we assuming that all the keys are created at the exact same time? Because, for example, if one is started at time 0 and the other is 400, then the other 400 has only 100 milliseconds to...
Great question. Great question. So the question here is, what's the consequence of doing it this way, right? So what you're really doing, what's the consequence of having one timeout that handles everything in terms of the granularity of the timeout? So what we're really doing here is we're trading less space for less timer precision. So before, the way it worked is we had, each key had very relatively precise timer precision, assuming that the scheduled executor service works right, and it does. So if you said, I want to schedule this thing, it would go off at roughly, however many milliseconds in the future. In this version, whenever something gets put in the map, the next time the whole thing runs, it'll go through and clean them all out. So you might end up in a situation where you would purge stuff faster under this model, under the one thing. But it's classic kind of precision space trade-off, if you will. The reason why this works, of course, is because, or the reason why this conceivably works is that cached values are just a hint, right? So they're not really changing the meaning of the computation. It's just changing how frequently things get run. Yeah, that's a great observation, though. So the good news here is you can pick whichever one you want. So you can do experiments and choose one or another. Any other questions about this? So I guess the moral of the story is continue to learn the features that are built into Java, because there's all kinds of stuff in there that help to make your life a lot easier once you know that they're there. So stuff like the get an update method, which is part of atomic long, the stuff we were just talking about that had to do with compute if absent. Those are things that are good to get to know and learn. And the other moral of the story is these really fine-grained locking mechanisms are very efficient, but they often require thinking carefully about how to design your program. It's much easier to reason about a program that just grabs a synchronized statement or a reentrant lock at the beginning, does a bunch of work, and then releases it at the end. Much easier to reason about your program if you do that. The problem there is that you're going to end up having scalability problems on modern multi-core processors. So these very fine-grained techniques you find with the concurrent collections that Java has are much more powerful and much more efficient and scalable, but they often require some thinking because you can't lock stuff for a long period of time or over a broad span of code. OK.